Good morning, everyone. Thanks for joining this webinar from wind to hydrogen, technical and operational challenges. So in this webinar, we will cover some of our research activities as a part of the Hydrogen Innovation Initiative Program, or HI. HI is an Innovate UK funded program, a partnership of the 13 UK leading organizations, including Offshore Renewable Energy Catapult. So the aim of the HI is basically to accelerate the key technologies related to hydrogen, translating research into impact and helping us to basically build a future-ready hydrogen ecosystem. So in this webinar, we have 4 presentations, all of these presentations covering different aspects, technical and operational aspects of the production of the green hydrogen and also the use of the hydrogen using wind. There will be time for the Q&A session at the end of this webinar, which we will give you some time for any questions that you have. And with this, I will pass it over to our first speaker, Dr. Yunus Tunga, which will be talking about the harnessing wind and hydrogen project insights and key findings. Thank you.
Thank you, Shahruz. Good morning, everyone, and thank you for joining this session. My name is Ines. I'm the practice manager for the renewables practice at the Energy Systems Catapult. I have about 10 minutes where I'll provide you with a brief introduction of what the Catapult is about, some of our capabilities and the role that our role into the hydrogen, our role into investigating the role of hydrogen in providing flexibility and resilience for the UK energy system. So please note the primary objective of my presentation is not to delve into the details of the scenario insight, but we will be sharing the reports that are now out that provide those in details. So it's very much to highlight and indicate some of the complexities and interconnected nature of the systems, and also kind of emphasizing where we are with our goal to clean power 2030 and the net zero by 2050. So I'll discuss a couple of studies where we explore within the HI project, the Hydrogen Innovation Initiative. Apologies. Shahruz, if you could go to the next slide, please. Thank you. So a quick one on who we are. The Catapult Network is a network of 9 different Catapult networks. Our objective, and we are a research and innovation focus in different fields. The map on the right provides an overview of the different centers, from Sales Engine, Connected Catapult. We have the satellite, offshore renewables, and as the energy systems, as well as digital. The main role here is to accelerate net zero, and to do so by supporting by providing technical capabilities, opportunities for innovators, and bridging the gap between academia, industry, and government. And on the next slide, I'll give you a few words on what the Energy Systems Catapult is. Our mission being to accelerate net zero energy innovation, and these are some of the areas that we cover. It's mainly based on the core part of emerging and future energy systems, and we help inform the overall potential for these areas, opportunity and challenges, and also draw out pathways to successful deployment and integration of the wider energy systems. So expertise is mostly in the whole system thinking, where we join up the whole system from your source of energy to the consumer. We break this down into different silos to understand the different parts and the different interactions, and also the physical requirement of this system, as well as your policy, market, regulation, and digital arrangement as well. So on the next slide, it's a quick overview of some of the tools and all the assets that we have. But we have one of the models that we use, the energy system modeling environment that we call ESME, and that gives us insight into to support the understanding the least cost of technologies, or least cost of technologies that will meet the net zero. And from the energy, the ESME, that feed into our regional tools, our local tools, and building as well. So here, again, I'm going very fast on these, but this is very much to highlight that when we think net zero, when we think hydrogen, it's not just at national level. There are different levels and different granularity, if you like, into which we need to consider the role of hydrogen, but also the energy system into how we deploy this to inform policy, to inform local authorities, etc. Moving on to the next slide. Thank you. I thought I'll pause here for a minute, and there's a lot on this graph, but what I wanted to highlight here is we have about 25 years to decarbonize, to actually deliver the net zero. So that's 25 like to deploy various technology at scale in volume. Some of these are already well established and low regrets, but it's the implementation. We need the space, we need the volume to actually get us there. And to do so, we did some analysis with some of our tools and some of the insight internally. But a lot of the challenges, and this is only to name few, is the electricity network reinforcement. It's one of the biggest risks really to decarbonization journey, because we still need to maintain the security of supply. So we are going to continue to generate, but we need our electricity network to actually keep up and being reinforced to actually take on all the energy and all the energy that is produced. Another thing that we all know, we know offshore wind and onshore solar have already already have a huge role in our current, but also future energy systems. But there's the challenge that this need to be deployed at scale, but it also need to be produced when it's needed. Hence, one of the reasons why Sharon's touched on why the HIGH project, why are we doing this? So in practice, the energy mix will require network reinforcement, but also grid stability, market regulation, supply chain, and others as well. So this graph touch on, we know that the dispatchable electricity generation is decreasing as we get more and more renewables into the system. That's then require a significant work into flexibility, and hydrogen will be one of the elements that could provide the flexibility for our energy system. So the next slide will kind of touch on some of the work we've done trying to estimate the demand of hydrogen in the UK system. When we started this piece of work, we realized that we need to improve first the data representation of the various demand sectors and hydrogen technologies that we either currently have or that we focus to have. So within the HIGH project, we developed new data sets and models, and we use this to analyze the entire energy system. And this analysis explore different scenarios to understand where this hydrogen technology might be deployed in the future. So we have the four scenarios here, so the various pathways, each with different policy choices, each with different technological characteristic, and the value chain as well related to the hydrogen value chain. So essentially, the four scenarios here were created to test different future possibilities for the UK hydrogen landscape. Now, each scenario represents a different world, really, where how well the technology innovation is coordinated, how quickly it can be achieved. And this move from one end of the spectrum where it's pessimistic, where innovation is stalled, commercial viability is delayed by 5 or longer than what we currently expect, to the more positive on the right, where hydrogen optimism, where innovation progress is rapid, commercial viability is reached within 5 years ahead of our expectation. And this is for us a way to test what does the future energy system will look like. Again, there is a report that is already published that we can share the link at the end of this webinar. And on the next slide, we touch a little bit on what does this, sorry, I think probably, if you go back to one slide, I think I probably hide the slide. So I suppose the aim of this scenario analysis is to understand the annual demand for hydrogen. In all scenarios, even the pessimistic view, hydrogen will still play a significant role in the energy system. However, knowing the scale of this will depend very much on the policy, on some of the investments, on the technology advancements. But it's definitely the case that the hydrogen will we will have some hydrogen deployed by 2030. There's then a question on the off-takers, etc., that my other colleagues will cover. And the next slide touch on one of the, thank you. The next slide touch on one of the other tasks that we did as part of this study. So looking at the hydrogen demand scenarios that I touched on before, we started looking at if grid reinforcement or network reinforcement is a challenge, can we explore the potential for co-locating offshore wind with electrolyzer? So this is one of the cases that we looked at, the use cases where we look at co-locating offshore wind with electrolyzers, where we wanted to assess the techno-economic viability, but also the system impact of these hybrid connections. So we developed this model and used it to evaluate the impact of adding green hydrogen to pre-existing offshore wind. Not only that, but in the future to a hybrid system being installed. So understanding the design that need to be done to optimize the size and the dispatchability of generation, but as well as the storage and all the conversion technologies as part of that. So what the model help us with is to determine if it's viable. When is it viable to consider collocation and the different type of site, especially when there's electricity network constraint. Some of the inputs, some of the parameters as input were the techno-economic features, so your CapEx, your OpEx efficiency, but also the range of technology scales available for optimization, weather, of course, resource, and the price profile. Now, based on these inputs, the model then provides the size and the dispatch hour by hour operation of different systems, and that then maximize the economic viability of the site. So it's a side-by-side basis, so looking at some of the specific within the site, and also provide the boundaries of the techno-economic system. So I'm not sharing any data or any result because this will be very specific to the site, specific to the operation conditions. But we have a report where we highlight some of the assumptions. It's worth noting, and we know that already with different renewables, that pricing mechanism will be different, aspect of demand and exports will also be different, especially for hydrogen. So that's one of the use cases. And the next one I wanted to touch on the next slide was a work that we completed with Ricardo to develop a comprehensive study. The objective here, we want to understand where in the UK can we deploy large-scale wind facilities that can be coupled with water electrolysers. Again, the understanding here is, can we provide a narrative on the trend, on the size of the site where the geographical constraints are considered, where the critical infrastructure and infrastructure requirement are considered. This includes storage, water requirement, grid connectivities, etc. Again, this work was really interesting because we did that on the back of the U-turn on onshore wind in England. So that provided more information on the sites that could be considered for collocation or for wind with water electrolyzer. And the next slide really emphasizes bring all the constraints together in the map that we have on the right-hand side. So that from the water, the wind speeds to the different constraints onshore as well as offshore with the water depth, etc. So there are significant amounts of potential onshore and offshore, and I've highlighted on this slide some of the sites that we saw as with high potential. This is considering the critical infrastructure requirements and the different aspects. We also touch on water scarcity, water requirement here. I believe on the next slide, and just to conclude, we will be sharing some of the report that are already published, and we're happy to take some further questions. But as final thought, really, renewable integration is only sustainable if we consider the storage and flexibility aspects. There are still a lot of challenge that we need to consider when it comes to the network and reinforcing the network, but there are some solutions that we can consider now while this is also happening. So happy to take any questions, and over to you, Michael.
Yeah, thank you very much, Ines. That was brilliant. Thank you. So yeah, I'm Michael Walsh. I'm a hydrogen systems engineer working at the Offshore Renewable Energy Catapult. Today I'm going to talk to you a little bit about some of the challenges associated with integrating green hydrogen systems. I'm also going to go into a little bit of detail around the Hi-Fi facility, which is a fully integrated hydrogen system brought to our Blyth site. I'm going to try and cover some of the motivations behind bringing that facility to site, some of the sort of basics around the hydrogen economy, and then it's the challenges of integrating the hydrogen economy, and then yes, finally, how that all relates to the work we're doing with the Hi-Fi facility. Next slide, please. And so just a little bit of housekeeping when we're talking about the hydrogen economy. We're talking about the use of low carbon electricity from renewables and nuclear, used to drive electrolysers and separate water into hydrogen and oxygen. That hydrogen is then distributed around the economy using different transport methods, pipelines, and compressors. And there's a requirement for conditioning of hydrogen along the way to ensure purification and sensing of that hydrogen. This is then fed into industrial or power sectors and potential opportunities commercially or residentially. And I just want to highlight some of the outputs of the Hydrogen Innovation Initiative's Hydrogen Innovation Opportunity Report, where it sort of details that the two primary drivers for an investment in a hydrogen economy are first the opportunity to decarbonize the domestic industry using hydrogen, whether that be like-for-like swap for grey hydrogen or fossil fuels, but also the opportunity to capture a share of the global hydrogen economy through developing expertise in key technologies such as electrolysers, compressors, and different use case technologies. And to break those like economic benefits down a little bit further, there is then the sort of direct economic value that can be generated from hydrogen production and engaging in a wider hydrogen market, both through the technology and actual sales of hydrogen itself, but also then the infrastructure that surrounds that. But there is also the indirect economic value, which is key to this innovation opportunity report. And this is the opportunity for industrial activities and development of industrial clusters and what economic value that can provide to the UK economy more widely. And this report has done a pretty good job of sort of estimating the scale of that opportunity on the next slide. So the scale of this opportunity, broadly, when you look at some other reports that mainly focus on the opportunity of the direct value, you come to a figure around 4 to 6 trillion for the global hydrogen economy by 2050. This report also includes some of the opportunity associated with the indirect value and estimates that figure to be closer to 8 trillion by 2050. And a lot of this is locked up in the production, distribution, and use case technologies. And so what's been done here is a sort of breakdown of what the strategic areas of opportunity are. So what technologies, i.e. in production, propulsion systems for transport, using hydrogen as a feedstock, but also then how the UK can strategically position itself in key areas of expertise to capture as large a proportion of that market as possible. And so we're going to focus here around the sort of 4 key areas that are highlighted in this report. The first being distribution and control. So this is, again, talking about how we move that hydrogen around an economy, how you optimize the use of pipelines, how you optimize your conditioning and control of renewable assets and hydrogen production plants. The second is that conditioning piece, so where multiple stages of compression and storage will be associated with a hydrogen economy when moving power from decentralized production sources to centralized utilization. The third is this sort of electrical and thermal management. So as we move towards electrified grid or a larger electrified grid backed by renewables, the management of electrical conditions to ensure secure and reliable supply of electricity is met, but also thermal management. For example, with electrolyser plants, there's a significant amount of thermal heat generated, and it's what opportunities are there for integrating that with industry or plant control. And then finally, the sort of monitoring and measurement economy where new sensing technologies are required to ensure the safe and reliable supply, to be able to detect leaks, but also measure the quality of hydrogen as it's shifted around an economy. And this report sort of highlights where the sort of underpinning dependencies are to be able to capture that part of the market, and how we can utilize existing expertise in the UK in material science for membranes or different storage materials, this digitization piece around the control of renewable assets and power infrastructure and electrolyzer units. There is a significant opportunity for growth in skills, whether that be from construction of these facilities and the infrastructure associated with it, right the way through to engineering practices and scientific research in the field. And then finally, this piece around batteries, as we see this becoming a larger and larger part of how you balance an electrical grid, it's also very important in how you balance power for hydrogen infrastructure. And so that's all well and good talking about the opportunities, but what are the sort of barriers? And so on the next slide, there are sort of three categories, or I've broken down some of the main barriers to hydrogen economy into the supply chain, integration challenges, and green hydrogen offtake. So for supply chain, if you could just click Shrews, please. I've drawn this from the Hydrogen UK's Hydrogen Supply Chain Strategic Assessment Report, which does a really good job of assessing key technologies that are going to be required as part of a growing hydrogen economy, where the existing supply chains may lie within the UK that can meet that demand, how they are meeting existing demand, and where SMEs or companies that are already within the energy sector might be able to transition some of their expertise and pivot into the hydrogen market, and where the growth opportunities and the existing expertise sort of align. They are considered to be high strategic significance. So, for example, electrolyzer stacks and hydrogen compression, which is significantly important for the growing hydrogen economy. We already have expertise in these fields, and it's how we can then scale those manufacturers or scale those technologies to be able to meet future demand. And similarly, power electronics and high voltage transformers, where for a growing electrical grid backed by renewables and the efficient transfer of electron molecules to hydrogen, there needs to be a growth of these industries to be able to meet the future demand or the supply chain. And essentially, this report just sort of details how and where we can strategically position ourselves to meet that demand. The second is integration challenges. And so this is what we're a little bit more interested in the hydrogen systems team at RE Catapult. From experience with working with hydrogen systems, we can see that there is a lack of clear regulation at times, both in defining the testing and validation of key infrastructure such as electrolyzer units, and how we can ensure reliability and how we can inspire confidence in those technologies for the rollout of green hydrogen systems, but also clear regulation around some of the use cases for hydrogen, where in some cases it's seen as a bit of a Swiss Army knife, where we can actually target specific industries that would be able to benefit from hydrogen production the most. And some of the incentives from government or regulation around, say, blending and how they can drive that growth. There's also a lack of experienced integrators. So as we transition from where hydrogen is typically being produced by steam methane reforming of natural gas, when we move towards using green hydrogen technologies in decentralized locations and away from steam methane reformings on industrial clusters, there are a lot of integration barriers in moving that hydrogen around and producing that hydrogen. And because this is at the confluence of electrical, mechanical, and chemical sort of disciplines, it's difficult finding experienced integrators to be able to bring these systems, these complex technologies and systems together. There's also a requirement for novel technologies in all of these cases, whether that be novel electrolyzer technologies, new sensing equipment, developing balance of plant that is specifically designed for hydrogen production, such as power electronics. Because we're introducing lots of novel technologies within the same systems, there is an increased risk associated with moving towards this infrastructure. And then finally, there is a set of sort of technical challenges that need to be overcome, mainly around sort of power management and molecular flow management and heat integration for the various different systems, but also technical challenges as part of the transition. For example, grid forming capabilities, where current infrastructure will utilize two-way HVDC cables to kickstart offshore wind farms. If you are to replace this infrastructure with hydrogen, how can we actually deliver that power to be able to form a grid and begin production? And then the final piece around green hydrogen offtake. So this is sort of coined the chicken and the egg problem, where to grow the infrastructure to the scale that it needs and provide that secure confidence to be able to invest, we need to secure offtake. And there are sort of two opportunities. The first is reducing the levelized cost of hydrogen so that it can compete directly with grey hydrogen or other fossil fuels within industries that already utilize these technologies, but also capturing confidence in industries that don't necessarily already use hydrogen, but might want to transition to it as part of a decarbonisation plan, and how we instill confidence in those projects to be able to obtain that initial investment in infrastructure, which can be quite expensive, especially such as like transport, storage, and utilization of that actual hydrogen. And so that's laying out sort of the barriers and some of the challenges with the hydrogen economy. And so what we're trying to do at ORE Catapult, or one of the routes that we are approaching to kind of tackle some of these challenges, is to bring a hydrogen system to site. So next slide, please. And this fully integrated hydrogen system, Hy5, has been brought to the Blyth site, and essentially it is a containerized solution in which there is a centralized rack within that container that has 5 kilowatts of electrolyzer capacity. So we're talking about R&D levels of infrastructure. That hydrogen, the power is fed into the facility through a power management system that works with a battery and an inverter. There is then a piece around managing the power flow to the electrolyzer and how we would transition to potentially powering this without a grid connection, but directly from renewables. There is then looking at the challenges of conditioning. So when the hydrogen is required to then be separated and dried before it is then fed into storage. And as you can see, we've got a separate hydrogen storage vessel outside of the container, which can reach maximum pressure of around 35 bar and store around 3.5-4 kilos of hydrogen. This can then be fed back into a fuel cell that is located on site or within the container, and that power can either be fed back into the battery storage system and reused as part of the power management, or can be fed back onto the local network connection. And if you could just go to the next slide. And so looking a little bit more detailed at a top level process flow for the facility, we can begin to understand what some of those technical challenges are and why it can be so complex. So there is this question around power management. So currently we are grid connected to the site electricity supply. However, to move towards green hydrogen, we're looking for integration with renewable assets and how you optimize your power flow and potentially build in fuel cell capabilities so that you can reuse some of the hydrogen to manage your power flow further down the line when there is a period of low energy production. There is also this piece around water supply. And so currently the system is air cooled because it's small in nature. But as you move to larger systems, and especially electrolyzer plants, there is going to be significant amounts of heat generated. So there's this piece around how you can work with local councils and local utilities to ensure that there is suitable water supply without impacting the supply of potable water to local communities. There is another piece of work being done around sort of optimization of control and sensing equipment. And so we have two sensors, one inside the rack and one external to the rack. And how you work out how you can locate these things to reduce the overall requirement for this infrastructure, but also how they can be sort of utilized to reduce or impact your ATEX zones. So you can see we have an ATEX zone external to the hydrogen tank, but there was also the chance due to leak that we might have to have an ATEX rated zone within the container, but we were able to suitably optimize the ventilation so that we could reduce that ATEX zone. And so the impact that had on infrastructure, not having to buy H2 sensors, ATEX sensors, sorry, and ATEX ready equipment, significantly reduced the cost. I just want to draw your attention also to this list on the right, which is a sort of more detailed list of the components within the container. We've used two Inapta AEM electrolysers. And so these are, AEM is anion exchange membrane. It's a lower TRL technology, which aims to combine some of the positives of the industry standard for renewables, which is considered to be proton exchange membrane, with some of the positives from traditional alkaline electrolysers, in which there is a reduced cost associated with them due to the lack of reliance on platinum group metals. And so we're particularly interested in this, the AEM technology specifically, and how you can optimize operation around that. And so there are some of the sort of technical challenges we're trying to overcome. The next slide will look into some of the how safety, health, and environment have actually driven the design of the facility, and how they've actually impacted, how they can actually significantly impact, the economic viability of your project. And so, as I've already mentioned, we did a DESIR study to be able to bring the facility to site. And part of this DESIR study is identifying the hazards associated with hydrogen infrastructure, and determining ATEX zones for the facility. And like I said, as part of this study, we were able to determine that the leakage within inside the container, if there was to be a leakage event, could be suitably managed with ventilation and didn't have to have an increased ATEX zone within the container, and this reduced the cost of the infrastructure required in the container. For those of you that aren't aware of the Blythe site, the Blythe site is also central to lots of other testing and validation infrastructure. And so there was an interesting piece around this PSSR and ensuring certification and that component safety limit were suitable for being in an industrial location. And this had a significant impact on how we minimized the footprint of the facility, whilst also maintaining safe operating zone and reducing the impact on surrounding infrastructure if there was to be a leak. There was also a lot of work generated around risk management, around site operation and maintenance. However, we'll leave some of this here because I think Ed will be talking about this process a little bit later on. And if we could go to the next slide. So here are some of the other outcomes associated with integrating the facility. Just wanted to bring your attention to one of the main ones here, the encryption and remote control access associated with the energy management system. And so a lot of the manufacturers of electrolyzer technologies are very interested in the chemistry associated with the cell and how you improve the efficiency. And what we found when bringing the energy management system and the facility to site was that potentially the encryption of that control system when looking at remote control access and turning the system on and off wasn't necessarily in line with the sort of top level directives on encryption. And so we worked with a third party and a supplier to be able to improve this. And obviously this becomes a significantly more important piece as you move towards larger scale plants and reducing the risk of threat or attack on these digitized facilities. And then our sort of future areas of interest and how we want to progress with the system, we've got the learnings from how you bring hydrogen systems to an industrial site. We now want to start sort of testing the system. And so some of the key areas that we're interested in are this optimization of heat management and system cooling for larger systems, how we can potentially use that heat for integration with industrial activities, but also how it can be used to reduce the cost of idling the electrolyzer itself. There's this integration with microgrids piece. So when locating batteries, electrolyzers, and renewable sources on the same site, how can you optimize their operation to allow you to increase the lifetime, but also access other streams of revenue, such as grid balancing processes. And then finally, we're looking at this moving to a larger plant system. How do you optimize the centralized control where you have multiple stacks and you want to maximize the lifetime and minimize the efficiency penalty associated with operating multiple different stacks? And then I guess the sort of next steps on the next slide for the facility and how we're actually going to deliver some of those learnings is we have these sort of like three interest areas that all sort of feed into each other. And so we want to develop electrical equivalent models that will capture the behavior of the electrolyzer stack. We would like to then test the sort of electrolyzer as part of the hardware in the loop asset testing we have on site. And use some of the learnings from that to verify the models even further so that we can take the electrolyzer out of the testing loop and use additional balance of plant and product development without actually generating hydrogen by using verified models to sort of replicate the electrolyzer system. And so all these activities sort of feed into each other, which I think might quite nicely lead on to what Anup is going to talk to you about. So Anup, if you'd like to continue, but thank you for listening and we'll take questions at the end.
Thank you very much, Michael. Good morning, all. My name is Anup Nambiar. I work as a research engineer at the URI Catapult as well. My area of expertise and focus is on grid compliance. So I'll be giving you all a brief overview of some of the electrical challenges and considerations we need to make when we try and integrate green hydrogen production with offshore wind power. So I think that's going to be the key part of the next 15 minutes or so. Sharers, can I have the next slide, please? So I'm going to start with, again, a relook at the background and context. I think both Michael and Ines before me have already given you all a comprehensive overview of why green hydrogen. But what I'm going to do is put a power system perspective in there as well. We'll look at some of the integration topologies that are being considered today to integrate offshore wind with green hydrogen production. Look at what grid compliance is, what grid codes are, and what the requirements are within today's grid codes on operating such integrated systems. And then what the new technologies that we've already seen today so far and the grid compliance requirements mean is that there is a need for more robust validation and testing. So that leads on to the last part of my presentation where we look at what the motivations are for testing and validation, some of the test approaches, test types and test approaches that we're developing at the URI Catapult for hydrogen system testing. And that, as Michael said, that ties in neatly with his last slide there. Can I have the next slide, please, Sharus? Yeah, so the background is something that we would all accept that green hydrogen has a critical role to play in us decarbonizing the UK. by 2050. And it's especially the case to help us decarbonize difficult to decarbonize sectors like heating, as an example. And there are also industries that use hydrogen as a raw material that Michael's alluded to earlier. So if we need to decarbonize those sectors, we need green hydrogen production. Now, what green hydrogen does is, in a grid where we have a large penetration of offshore wind, as an example, green hydrogen gives us some flexibility to operate the system better. And it's especially important in areas, for example, where we have a significant wind resource, but we don't have the grid with enough spare capacity to take in all the power that these wind farms are producing. So that's the kind of power system context in which I'll kind of base my presentation. Next slide, please, Sharus. The next one. Thank you. So we start with, how do we integrate wind farms or wind power with green hydrogen production? There are three main topologies that are considered here. The first one on the top, topology 1, is onshore centralized. So I think that's where we have a conventional wind farm operating offshore. The electrolyzer and all hydrogen systems are onshore. So that's onshore centralized topology. The second one there is offshore centralized, where your electrolyzer is offshore on a substation, on a platform. So the collector network in your wind farm stays the same like before. It's an AC collector system that we have, which powers the electrolyzer on this platform. You don't have transmission cables in this topology. It's hydrogen that's transported through pipelines to the shore. So it's offshore centralized. And the third one in the image there is offshore decentralized, wherein we have an electrolyzer at every wind turbine and someone's balancer plant as well. And in this third topology, we don't have any transmission cables or collection cables at all. All energy transport happens through hydrogen pipelines, which you can see in the image there. So can we go to the next slide, please, Sharus? Thank you. Now, if you go into a bit more depth, these are some of the characteristics of the three topologies we've just seen. So onshore centralized, as I said, it's closest to a conventional wind farm operating. So it is a grid connected system, both the electrolyzer and the wind farm, which means that the equipment need to all the equipment connected need to comply with the grid codes, and you potentially can also provide grid services to the power system. And because we've widely used, or we've got a large number of wind farms and electrolyzers connected to grid operating today, there's a pretty high maturity system that we have there. For both the offshore topologies, though, I think the key aspect there is that both these are off-grid systems. So if you look at the image on the right, the electrolyzers don't have a connection to the grid. And what that means is when you're off-grid, it gets challenging. You still have an electrical system to contend with. There are issues around voltage and frequency regulation. There could be issues with controlling and managing stability within this electrical network. As I think that's something that Michael pointed to, we might need to incorporate some form of grid forming control within the electrical network to ensure that you have a voltage and frequency reference to operate at, which in turn means you might need some form of energy storage, which could be on the substation or on your platform in the second topology, or on the wind turbine itself in the third topology there. And considering the challenges in operating off-grid and having some of these novel technologies deployed offshore, what it means is that it's a relatively low TRL, low mature, relatively less mature system we're dealing with here. But that said, there is work ongoing. There are pilot projects, demonstration projects that are deploying such systems. So all these three topologies in the medium to long term have potential to be actually deployed and commercially developed. Have the next slide, please, Sharus. I'll move to grid code compliance for a moment. So grid code compliance is most relevant to topology 1, wherein your electrolyzer and the wind farm are both grid connected. Now, for those of us who might not know what the grid codes are, so essentially it's a document that discusses in detail what the technical requirements are for plants and equipment that connect to the transmission system. In the UK, the grid code is managed by the National Energy System Operator, the NESO. And why do we need the grid code? We need the grid code to ensure that we can operate our grid reliably and the grid's resilient. So we want to make sure that all equipment and plants that connect to this transmission network of ours complies with these minimum requirements. And what is grid compliance testing? That's the process through which, that's the testing kind of regime through which an equipment or a plant needs to go through to prove that they comply with what's in the grid code. So can we go to the next slide, please, Shiraz? Thank you. Now, based on our review of the UK grid code and our understanding of the EU regulations and some of the connection requirements grid codes across in the EU, what becomes evident there is that the requirements that generators, which includes wind turbines and wind farms, need to meet are pretty detailed and well defined because they've been around for much longer. Now, what becomes obvious when we review these grid codes is that the requirements on demand are far fewer and less onerous. And at the moment, electrolyzers are clubbed within this demand kind of bubble. But that said, the grid codes are continuously evolving. So there are working groups in the UK, expert groups in the EU that are looking at various aspects of the grid codes and how to improve them, how to make them more relevant to all the changes we're seeing within the energy system today. So as an example, so there was an expert group in the EU looking particularly at power to hydrogen or electrolyzers, and it is likely, and they've suggested that further technical requirements that electrolyzers need to meet would be included. They've suggested these to be included in future releases of the grid code. They are talking about electrolyzers potentially providing support to the grid during grid events. And there are also discussions around whether today's electrolyzers can meet some of these stringent grid compliance requirements like forthright through, and what some of the implications are there. And it's not, we're not looking very far ahead. Some of these changes are going to be introduced within the EU regulations this year. And it's very likely that these changes in the EU regulations are reflected in the UK grid code as well in the short term. Can we next slide, please, Sharuz? Thank you. So what that takes us through, so we've looked at challenges in operating this integrated system, wind farms, electrolyzers, especially when they're off-grid. We've looked at some of the most stringent grid code compliance requirements that these electrolyzers need to comply with. That's the two areas where there's been a lot of focus within UK industry and research. There's also co-location that Ines mentioned earlier on. Can we have wind farms, battery storage systems, electrolyzers connected behind the same grid supply point or connection point? And that provides flexibility to the grid operators, but that also, there are a number of challenges that we need to kind of solve before such systems can operate successfully in a grid, effectively in a grid. So we've got new technologies, we've got new combinations of technologies, systems formed by some of these novel technologies. We've got off-grid operation, and I think the kind of underlying message there is that there is a requirement for a lot of validation and testing to make sure that these combinations of technologies or systems and novel technologies work well within this wider system of ours. And that's where everything from software, hardware, and hybrid testing comes into the picture. Can I have the next slide, please, Sharuz? Thank you. Going one step back, away from hydrogen systems per se, what are the motivations for testing and validation? So you've got three buckets there. You've got legal obligations, so things like the grid codes. You've got safety requirements that you need to comply with. So one way of proving that your system complies with these is through test and validation. Your customer demand is the second bucket there. So if you are an equipment OEM manufacturer, you might your equipment would be part of a larger system. There may be other pieces of kit connected to it. You want to make sure your equipment integrates well with it. One way of proving operation there is through test and validation. There's a question of design confidence. So if you're an equipment OEM, you need to make sure that your device does what it's meant to do. It lasts for how long it's meant to last for, etc. So again, there's a question there on design confidence. And the earlier we find issues with our design and can fix them, the better it is economically as well. So you don't want your equipment to be in the market before you find issues which we need to then fix. So these are the three kind of buckets there for the motivations for testing and validation. If you go to the next slide, please, Sheroz. Thank you. Now coming back to our green hydrogen systems. So we've got the three topologies, and we kind of classified tests into these three classes. You've got functional tests, wherein the functionality of the various components within the system are tested. And you've got the integration tests. In this example, we're talking about wind turbine, wind farm integration with electrolysers. So that needs to be tested. Then we've got grid compliance for grid connected systems, grid compliance and ancillary service provision testing. So it's not a comprehensive list of all the different types of tests we need to do or can do for hydrogen systems, but these are ones we are most interested in. And you can see some of the integration tests are more relevant for the offshore topologies, which are off-grid systems, while functional tests are applicable to all of them. Can we go to the next slide, please, Sheroz? Thank you. So this slide gives you the different options that we have for testing such systems. So on the far right, we have field testing, wherein your system is deployed in the field. In the case of wind turbines, you run the wind turbine in the field for a number of months to a number of years even to get all the data that you need to prove that it's compliant to various codes. So it's high confidence, high cost testing there. On the extreme left, you have virtual testing, wherein you're basing your testing on numerical modeling approaches. Low confidence, low cost. What we have in the middle of system testing and hybrid testing, these are the two areas where a lot of our URI capital experience has been in. So with system testing, we're having the full system, but not tested in field, but deployed on a test bench and tested there. So you have controllability over environment, you have repeatability that's possible in the testing. Hybrid testing, the one in the red circle, that is what we are very keen to develop, and we are developing at the moment within the Catapult. So hybrid testing is the case where we don't have the entire system in hardware. So you would have parts of the system in hardware, parts of the system emulated in real time in software, and both of these coupled together. And if we go to the next slide, please, Sheroz, which is where I go into a bit more detail on what this hybrid testing looks like, what it is and what it looks like for this hydrogen system we are interested in. So the image at the top there shows you the four main components that we need to have within a hybrid test setup. So you need a mathematical model of the system that you're emulating in software, which operates on a digital real-time simulator. You've got the power amplifier, which interacts with your simulator and the hardware under test. So your control signals from the simulator get converted to real power signals, voltage and currents that go into your hardware under test. You've got measurements at the hardware side being fed back into your controller that closes the loop. So I think that's a generic hybrid test setup. Now, if you translate that to our green hydrogen production case, integration of electrolysers with wind farms or wind turbines, how would that look? So again, you have the four components. You've got the mathematical model. In this case, it could be the model of a wind farm or a turbine that you're interested in. So you've got the model there. We run the model on a real-time simulator in real time. The real-time simulator interacts with the grid emulator or a power amplifier, which is in the red box there. And you've got the hardware, which is on the right. So you've got the electrolyzer there, it's the power converter and some hydrogen storage. So that the hardware is connected to our grid emulator or a power amplifier. And the hardware works as though it is connected to this wind turbine that we are emulating in software. And again, you have signals, you've got measurements from the hardware side going back into the simulation on the simulator. So this is the area we're developing at the moment. So we've already done a lot of work developing component models, the stuff that Michael showed us earlier about electrolyzer models. We've got other component models that we've developed over time, validated with measurements. We've got a few real-time simulators that we have been using within the company. We've got the two grid emulators or power amplifiers. These terms are used interchangeably. So eGrid, that's our bigger grid emulator. That's an 18 MVA system that we have predominantly used for grid compliance testing of full-scale wind turbine cells. And we also have the smaller grid emulator that we call mini eGrid, which is a 1.2 MVA system. It's very modular, flexible, and can be used for both AC and DC system testing. So yeah, so that gives you a flavor of how we might run these hybrid tests for such green hydrogen systems. Go to the next slide, please, Shahruz. To quickly summarize, where we started from was the background, the role that green hydrogen has to play to manage some of the challenges we're facing within the power grid today. So there is a need for an additional energy vector that gives them the flexibility. We looked at three integration options for wind power and green hydrogen production, and we noted that onshore centralized, where everything is grid connected, is the most straightforward one at the moment. The off-grid topologies, there are a few more challenges, a bit more of testing and validation required there. And we looked at grid compliance and some of the most stringent compliance requirements that are coming for electrolysers in the next few months, which means, there's some additional technology updates that are potentially required, some additional testing validation required there to prove that these comply with the grid codes. Then we moved into testing. So we looked at why we need testing. It's all the newer technologies and systems we are trying to plug into our power grid, the types of testing that we are interested in, and the types of testing that we can do. The options that we have between in-field, virtual, and hybrid testing in the middle. And we had a brief overview of some of the hybrid test capabilities that URE Capital have, and some of our plans looking ahead. So that is all I have from my end. Thank you so much for your time and attention. What I will do is hand over to Ed, who's going to talk us through some of the safety aspects with hydrogen systems. Thank you.
Hello. Thank you very much, Anup. My name is Ed McFarlane. I work for safety engineering consultancy called Abbott Risk Consulting. We cover a number of regulated sectors, but of interest today is our work that we've been doing in the energy transition area. Done a lot of work around lots of other technologies, including battery systems of various types, but there'll be a focus here on hydrogen safety. And this presentation is based on a training package we developed for OREC to introduce people to hydrogen and safety considerations associated with that. Next slide, please. We'll quickly run through and just an outline of what I'll present you is kind of the intent of the package, what it is and does and doesn't do. Quick overview of relevant hydrogen technologies that influence the safety considerations. A quick summary of hydrogen, its characteristics, and then a run through the kind of principal legislation and guidance that's available, principal hazards associated with it, and just what general good practice around hydrogen safety looks like. And then we've got a range of guidance resources that will be available with the presentation, but provide you jump-off points to go and look at further detail. Next slide, please. So this training package, it really is just an introduction. It's intended to give you a consistent baseline of knowledge around hydrogen systems and the safety considerations. Hopefully gives you some consistent terminology and terms used, and really it's a stepping point for further information and training to follow up on and apply to your specific projects. Next slide, please. So in terms of the technologies, really we run through the kind of steps which Michael talked about as well. So broadly speaking, there's kind of two principal technologies for hydrogen generation currently. Thermochemical, so this is sort of steam methane reformation, biomass gasification, or sort of a solar thermocouple hydrogen, really it's thermochemical generation of hydrogen, or we have electrolysis. And broadly speaking, that is primarily PEM, proton exchange membrane, or alkali electrolysers. There are other electrolyzer technologies, but really those are the two principal means. And there are other ways of generating hydrogen, but really at scale, these are the technologies available. Next slide, please. So in terms of kind of storage, in terms of once you've generated your hydrogen, typically electrolyzers are producing or providing the hydrogen at 35 bar at their outlet. And really, we're kind of the main forms of storage are really so compressed, cryogenic, and cryocompressed. So compressed gas is fairly typical, compressed to high pressures, very high pressures in comparison with most other systems. So 200, 350 bar, and 700 bar are typical ranges. Cryogenic, which is just chilling it to the point where it liquefies, but very, very cold temperature. But there is another technology, which is cryocompressed, which sits somewhere between the two, which is slightly higher temperatures, but it's still at significant pressures. And broadly speaking, for these kind of technology, we have two broad storage technologies. We have compressed gaseous cylinders, and there's 4 different types, depending on how they are manufactured and designed. And then we have cryogenic or cryocompressed tanks, which obviously have fairly significant insulation requirements associated with maintaining the liquid hydrogen. Next slide, please. There are other storage technologies. Solid state storage, so this is broadly speaking sort of metal hydride or absorbents, but this is storing it within a material that either absorbs or kind of has high surface area and has some sort of surface contact with the hydrogen and stores it. We have chemical hydrogen, so we convert it into another energy vector, typically ammonia or methanol, the two that are spoken about mostly. There are obviously other chemical derivatives or hydrogen derivatives that can be used. But then we have another class of storage materials, which is called liquid organic hydrogen carriers. And this is probably closer to how we think of hemoglobin, in that it reacts with hydrogen, stores it, but it will then release it as well without being actually consumed in the process itself. So broadly speaking, these are kind of the range of the different storage technologies. And they all have their own associated safety considerations. So typically, if you move from compressed gases to ammonia, you start to introduce sort of toxicity concerns and that kind of thing as well. Next slide, please. And really, that's kind of the generation, the storage, and then really it's the application at the end of this. And Michael covered most of these, but we'll just quickly run through them. So process industry, so use as chemical feedstock. Just as a pure energy vector, so we are just transferring it and using it as a transfer medium to elsewhere, which will then use it in one of these other applications. But it's really important to think about these different methods of using it as an energy vector. So individual cylinders, manifold cylinder packs, multi-element gas containers, tube trailers, and pipelines are broadly speaking the main ways these are transported. And then we move into this kind of actual application. So transport, so propulsion, which Michael mentioned. So planes, trains, and automobiles, these are all being looked at, considered for hydrogen. But historically, far and away the biggest kind of transport user of hydrogen has been rocketry for space applications, and primarily liquid hydrogen. There are other applications for hydrogen, so heat and energy. So you can take it as direct combustion or burners, into fuel cells, internal combustion energy generators, catalytic boilers, and combined heat and power systems that will use different ranges of these systems as well. But heat and energy, broadly speaking, are kind of another potential end use. But far and away, currently, it is the process industry that uses far and away the majority of hydrogen generated currently. Next slide, please. So hydrogen has some very specific characteristics. It's a well-known substance. It's well characterized, but kind of the kind of aspects that probably specifically of concern is it's very low density. So at atmospheric conditions, it can rise very quickly in air. It's very low viscosity, so it can leak easily. If there is a leak point, it will incredibly find that leak and leak. It also has very high diffusivity, so it can migrate through volumes and materials. So this can be a concern with sort of material embrittlement, this kind of thing. It has a wide flammability range in air. If you compare that to natural gas, it's considerably wider. But within that, you have the explosion limits. So the flammability limits and the explosion limits don't necessarily align. It's far closer with natural gas. And the other thing to be aware of is that even though that flammability range starts at 4%, the flame behavior is quite unusual. Right at that 4% limit point, it tends to just burn upwards. As you get to about 6%, it then burns upwards and sideways, and it's only once you get to 8% that really it burns throughout the volume of the released gas. Another really defining characteristic of hydrogen is it has a very low ignition energy. So very, very low in comparison to natural gas. And so this is where the concern around sort of static sparks can be considered. Its ignition temperature actually is not that far off methane, which is probably the nearest comparable thing. So it's really not hot surfaces we're concerned about. It is that low ignition energy. So things like statics, static sparking, or compression, we've got concerns with. It's often described as having an invisible flame. It burns at a very high temperature, which really emits in the UV range. So this means that although the actual flame itself is very hot, it doesn't have the same sort of thermal footprint of a comparable hydrocarbon fire. It does make it slightly more difficult to detect and spot, especially in daylight, but it is possible to get flame detectors, even infrared flame detectors that are tuned appropriately to detect these flames. But to the eye, it is far less visible than a comparable hydrocarbon fire, but with a smaller thermal footprint. It does have a very rapid burning rate. And this is probably the concern that most people raise, because with delayed ignition, you can undergo what is called deflagration to detonation, which are the two broad kind of explosion regimes. So we can get deflagration to detonation transition. And this is what people normally talk about when they say that hydrogen is really explosive. They mean it can move into a detonation regime, which is a very different kind of explosion regime than deflagration. Obviously, if we're talking about liquid hydrogen, we introduce a number of cryogenic hazards, and because of the very low temperature that we need to get hydrogen to become liquid, we do have the concern that we can condense out other gases from the atmosphere. And specifically of concern is oxygen, so we can actually produce LOX for sustained liquid hydrogen releases, and then we also got concerns about mixing the LOX with the hydrogen and potential source of explosion there. It's odorless, colorless, and tasteless, and it's not toxic. So there's a broad range of concerns. There's some other characteristics around its energy density, which we can discuss later. But broadly speaking, it's well characterized and known. This is all drawn from readily available sources. And it's really how these characteristics then influence our specific applications. Next slide, please. So in terms of general legislation, this is very much UK focused. The kind of main sort of items of legislation we should think about is the Pressure Equipment Directive, which really looks at the individual items of kit. The Pressure System Safety Regulations, which is how we take those pieces of kit and actually convert them or integrate them into systems that actually provide us with something useful. And the Dangerous Substance and Explosive Atmosphere Regulations, DESIR. So this is looking at small volumes, and really DESIR is focused on kind of the day-to-day normal operations. We then look beyond that kind of accident scenarios. And obviously, once we get to the offshore environment, there's additional legislation that is applicable. Obviously, all the other normal health and safety considerations will apply to the design and integration of the deployed hydrogen system. So it's not to get too focused on hydrogen to the detriment of other aspects. But broadly speaking, that's the main piece of legislation that we will be thinking we want to comply with. Next slide, please. Other things to consider, depending on the scale of your project, is hazardous planning consent. There's a threshold of 2 tons. So once you reach 2 tons, you are going to need to get hazardous planning consent for your installation. And if you already have hazardous planning consent, if there's a change that's greater than 2% of your current category, so 40 kilograms of hydrogen, you'd need to then do an update, and you need to consider it alongside other flammable gases. The next steps up the next sort of scale, if you start to look at COMA, which is control of major accidents and hazards, the lower tier starts at 5 tons, and the upper tier starts at 50 tons. And if we start to look at the transport and the movement of hydrogen, depending on how we're doing that, there's the overarching United Nations Committee on Transport of Dangerous Goods, on which all the other standards draw on. But ADR requirements, which is really road transport, and Transport Pressure Equipment Directive are applicable to most of them, and also the International Marine Dangerous Goods. So IMDG, if we're moving things by marine, and but obviously typical and other standards applicable for rail, transporting by rail. Next slide, please. So hydrogen isn't new. It has been used historically, especially in the chemical process industry. What is really new is our areas of application. There's existing legislation, standards, and guidance for hydrogen. However, all of those are being updated and developed in parallel to deployments. The sector is learning by doing. It's not really credible to just work to standard best practice. apart from some very simple systems, because that's not yet mature or established. And you may be working in a sector where sector-specific standards may not exist, so you may have to sensibly utilize the nearest comparable from an adjacent sector to help you structure your assessment. Next slide, please. So principal hazards associated with hydrogen is high pressure gas or liquids. So we can have debris, missile formation, pipe wick, direct gas injection actually damaging equipment, and also explosive decompression. So people often focus on the flammable aspects. Don't forget the high pressure gas concerns as well. Flammable gas, obviously, we can get an immediate ignition, which can result in jet fire if it's from a small leak point that has a sustained flammable gas jet from it, or a fireball. If we get a really large release in an unconfined environment, it can be ignited and the fireball can rise. If we had delayed ignition, we can incredibly get deflagration and potentially detonation if there's sufficient congestion and confinement. Or we can get what's called a flash fire, where a flammable gas cloud that's within flammable limits is consumed instantly, but with very little overpressure associated with it. And then if we're dealing with cryogenic hydrogen, obviously we have coal burns and embrittlement of equipment. So if we have a large release that goes onto a structural element, you can also get pool fires, and we can also credibly get what are called BLEVs, so boiling liquid expanding vapor explosions, where we have a cylinder or a container of liquid hydrogen with a pool fire under it, which is taken up to its boiling point, and then it reaches the point where it kind of releases a large amount of vapor instantaneously, which is then ignited. And as I mentioned before, the condensation of other gases. Principally, this is around LOX, so liquid oxygen. But obviously, if you've got a confined environment, sort of condensation of nitrogen or concentration of nitrogen can lead to low O2 environments as well. Next slide, please. So a really good practice is around design, so preventing it. So limit your inventories as far as practicable. Just have the inventories you want, but also split that inventory up into smaller sub-inventories, which then limits your size of your single release. But also don't forget, it's not just the kilograms of hydrogen you have, but also the pressures you're operating at. Reduce the pressure as soon as you can. Most applications don't want the pressure at hundreds of bars. They want millibars or atmospheric conditions. Minimize the potential for leaks. I know it sounds obvious, but you can do this through design by reducing as far as practical joints and connections and using all welded lines where practical. Make sure you go through appropriate pressure testing and validation of your system. And ensure through life insurance of that pressure envelope. Once you've done the work to really ensure that you have no leaks in your system, protect it. And then you're looking to how they then protect it. So especially looking at kind of drop loads impacts that can result in really large leaks. But obviously we can think about things like corrosion, erosion, vibrations, kind of mechanical ways that can gradually introduce leaks. So designing a system to minimize those potential and appropriate maintenance inspection to protect it through life. But also consider human factors. Valves that people can open accidentally to reduce releases, or ensuring that process venting is to a safe location. There was a review done for the HIAD2, which is Hydrogen Incident and Accident Database. Human factors was a significant contributor to that. Designing for overpressure scenarios. So this is really one of the ways we can get really large releases. So ensuring that when you've got different pressure regimes in your system, you segregate them appropriately and make sure that you provide overpressure protection. Think about kind of credible external fire scenarios that can overpressure your system. And then really thinking about your overpressure protection so that if you do start to see increased overpressure, you have both active systems, so you're monitoring it and you can mitigate and kind of intervene to reduce the relief, but also ensuring that you have passive, so mechanical, so passive, so burst discs or spring-loaded pressure relief valves, and keeping them independent, having truly independent layers of protection. Next slide, please. If you do have a release, so ideally you prevent release in the first place, you then really want to look at how you control and mitigate that. And as Michael said, one of the main things to do is just maximizing your ventilation. Where practical, put your systems outside to absolutely allow gas to escape. Where you do have containerized or kind of enclosed systems, ensure that the passive ventilation is designed appropriately to take advantage of both thermal convection, so elements generating heat and forcing some convection, but also the buoyancy of hydrogen. So normally this means that you want to have inlets to your enclosed environments down low so they draw in fresh air, and your outlets up high so that the buoyancy of the hydrogen will actually draw in fresh air to dilute down any released hydrogen as quickly as possible and any hydrogen release is then pushed outside of any enclosed environment as quickly as possible. You then look to eliminate and minimize ignition sources. And one of the main ones here is static earthing of systems. As I said, the very low ignition energy hydrogen is really important here. And you do that through, as Mike mentioned, ATEX zoning. So where you may have leaks in normal operation, you define a zone which you protect and then enforce and to ensure that we minimize the number of ignition sources within that, and or that they are appropriately rated to be used in that ATEX zone. And where possible, have hydrogen systems and lines elevated above other equipment as far as practical. Get it up high, take advantage of the buoyancy of hydrogen as far as practicable. Minimizing congestion confinement. So again, this is having systems outside as far as practicable and trying to really minimize other equipment around it that could introduce turbulence to any release. And it's only then do we start to talk about things like secondary protection. So there's firewalls, blast walls, or explosion relief. These are really one of the last barriers we should consider. And you really need to be very careful about applying them because they can actually introduce this confinement, congestion, and restriction of airflow through the site. To get these really large releases that require firewalls, blast walls, or explosion relief, we've had to have an awful lot of other barriers fail first. And really, it's very large releases. And really, we want to focus on dilution and keeping airflow through our systems as best as possible to remove any released hydrogen. Next slide, please. Then we obviously get onto emergency response. So detection, point detection for enclosed environments, or acoustic or other volume detection for outdoor environments. It is very difficult to detect hydrogen plumes directly. Any kind of air movement will move it away from the detection point. So you really, for outdoor environments, the point detection really isn't appropriate. Flame detectors appropriate for hydrogen flames. So as I said, they burn high temperature in the UV range, but you can tune infrared detectors to detect hydrogen. And what you're really detecting is the water produced by the hydrogen, by burning hydrogen in air and tuning the infrared detector to pick that up. Heat detectors, assume you've got jet fire impingement on something, but also audible leaks and penetrative monitoring. And then appropriate response, so shutting of inventories, operator restops, increasing ventilation, and audible and visual alerts and alarms to staff to move away. And then moving into emergency planning, so ensuring that we give first responders who come to site appropriate information, especially around hydrogen specific, and information about release times, access to systems that need to be protected, wetting with water. Next slide, please. So all that guidance has been based in part on these references. So these are all hyperlinked. So hopefully when you get the presentations, you'll be able to go and look at these in detail, especially for a lot of trial and demonstrator projects. The European Hydrogen Safety Panel has produced some really good guidance that is focused on kind of trial and demonstrator projects as opposed to full-scale commercial or early commercial. Please go and look at that. The basic considerations for safety of hydrogen systems lays out. I think that one is freely available from the ISO Society. It is not pay for one, so it gives you a good kind of overview. Next slide, please. And just to show what we're worried about here, this was an accident in Korea that happened at a sort of a science demonstrator park, a fairly significant accident. So next slide, please. I'll run through it. Thank you. So they ended up with O2 contamination into their H2 storage with a resulting internal static ignition and an explosion and detonation because it was a confined volume. 2 deaths, 6 injuries, and significant property damage. There were multiple failures of design against codes and standards. So this was a type of electrolyser that was known to be quite susceptible to O2 migration into the H2 stream. There was no system to scavenge or remove the O2 in the H2 stream. There was no O2 detection in the H2 stream. And the earthing systems were not inadequate, were completely inadequate. And so they ended up with internal sparking. But that's the approximate causes on the day, but there was wider issues. There seemed to be multiple safety management failures in the organisation, and also they were under significant pressure to complete testing, and maybe the view that it was a test platform. So please don't get too fixated on just the causes on the day. There may have been wider challenges, but really this is what we're trying to guard against. Next slide, please. So guidance sources, this is not a complete list. So it's to give you an overview that there is additional regulation and certainly ACOPs in the UK, so approved code of practice, which are a really useful resource, which are available from the HSE. So as I said, pressure equipment safety regulations, pressure system safety regulations, and pressure equipment regulations as amended, and transport pressure vessels, DESIR, and the equipment and protective systems intended for use in protection explosive atmosphere regulations. Next slide, please. Legislation that might be relevant, especially things like alkali. So there's a number of things around sort of substances you might want to consider. And then there's a whole range around transport of dangerous goods and transport in harbour areas. So hopefully there's a list there you can go to and use that as a starting point. Next slide, please. There's a whole raft of standards. This will be incomplete and out of date. There is standards in draft, working draft, about to be produced and provided by ISO, British standards, NFPA from the States, and AIP in the States, and EIGA in Europe. A really good resource is the British Compressed Gases Association, BCGA, who produced a whole range of guidance, which is freely available from their website, so please go and use it. I'll leave you to read that in your own time. Next slide, please. And here's a range of links from HSE research papers around hydrogen, both gaseous and liquid. Next slide, please. And here's some additional resources. So UK, so the Hydrogen Scotland, which is one of the trade bodies for hydrogen. We've got a safety forum group that we work within, the British Compressed Gases Association, and there are a range of other sources of active research programs looking at safety and legislation and regulation around safety across Europe. Hopefully a whole raft of useful information there. I'll point out especially the Presley and Elvis projects, which are specifically looking at liquid hydrogen, and the High Tunnel project as well, which are looking at vehicles in tunnels and producing a whole load of information. But all those multiple streams of active research looking at hydrogen safety. Next slide, please. And then a range of international sources, including the HySafe organization, which is the International Hydrogen Safety Organization, and then a number of H2 tools, which is based in the US, but provides a whole load of resources, as well as some free training resources as well, which can be used by people. Next slide, please. Thank you. Very quick run through.
Thank you very much, Ed. Thanks to all the speakers for the interesting presentation. So I think we got some time for the questions now. So if there's any question, please.
Few questions in the Q&A, but I don't know if Ines is, some of those are more to do, this probably Ines is probably a better place to answer than me, but I can provide some input if need be.
I was just touching on the cost benefit analysis. I was actually checking with one of my colleagues if we have any internally as part of the HY project, but I do know that the hydrogen strategy that was released in December provided some guidance into the cost benefit and the benefit of investing in those infrastructure. There's also another report that was out, the Hydrogen UK one also had a report looking at GVA by 2030, etc., including jobs and all those, but probably a question I'll take away and send further information if there's any.
I was just going to say, Ines, because we're both part of the INCOSE Energy Systems Interest Group.
Yes, yeah.
So in terms of sort of taking my safety hat off and putting my systems engineering hat on, one of the challenges I think is that an awful lot of people tend to look at these problems from the technology up rather than the systems down. And I think it's one of the things that often we see when we're looking at systems, that people forget what are often called like the non-functional components. So that's the things that aren't necessarily to do with just like the energy efficiency or the cost associated with it. It's the broader capabilities, things like resilience, safety, or the integrity and availability of systems. And we can't really look at technology. It's not like, is this better technology than this? It's like, well, what's the context? Until you've got that system context, like what we're trying to use it. And Michael made the point about hydrogen is often talked about as being a Swiss Army knife. It's a useful, once you've generated the hydrogen, you can then choose to use it as chemical feedstock or for propulsion, whatever. It provides very different capabilities from batteries or say heat storage. So you can get these really large, and really the reality is our energy systems are going to generally become a lot more complex. Which is one of the challenges for safety, is that we're going to have these very complex interactions. It's not just the technology, the individual technologies. So I would really encourage people to try and take that systems of view and go, which technology is most appropriate in this context? and actually using the systems beside each other. So we talk about domestic heating, it's heat pumps or whatever. So maybe actually on balance, a better system might have a bit of both.
Yeah.
So you may use on a day-to-day basis, say you're heating an industrial site, you may use your heat pumps for your day's sort of base load heating. And then if you have a cold snap, you have a hydrogen boiler that just tops up. And actually you can then optimize both those technologies far better than trying to have a heat pump that does it all, or having a hydrogen boiler that does it all. Actually using the right technology in the right context, it's not quite as simple as just this one versus this one. You need that broader context. I'll take my systems engineering hat off and put my safety one back on now.
And just to add perhaps on that point, there was a question on the battery, the comparison between the battery and the large storage. Again, we'll find this touching a little bit on your point, Ed. There are many studies that will start comparing or attempt to compare the cost of different technologies. But it's always tricky because if you start looking at the whole infrastructure requirement, they might not quite align, or they might not quite be relevant. For instance, battery storage is unlikely to discharge for more than 8 hours, whereas the other hydrogen storage might. So I think being careful as well on what we're comparing and what are the assumptions behind it will be quite useful, but I'll take that away as well, because I believe one of my colleagues is working in that space and might have some analysis to share.
Just adding something to that, Ines. In terms of the comparing the different technologies, so I think that we should be very careful. So these technologies, all of them valuable technologies, so we should not consider them as a competing technologies. Okay, so each of these technologies will play a different role within our whole energy system. So I know that, for example, thermal energy storage is very interesting, especially the high temperature thermal energy storage can play a significant role in our future energy system. Batteries as well, hydrogen can be also used in terms of the thermal energy storage system as well. So there's lots of possibility and flexibility. So we have to actually see it as a whole energy system and try to see which of these technologies best fit in a particular area.
Shall I quickly answer the question around the hydrogen and the gas network? So pipeline gas network is not my core safety area, but my understanding from talking to people who are doing it, there's an awful lot of research going into that. There's current restrictions on what percentage can be blended in, and absolutely, there's concern around stratification. If you've got a flowing pipe network, it shouldn't be as much of a concern. You're getting turbulence, which will reduce the mixing. And really, the concern are primarily around into the gas network is that the materials of the gas network. There's current programs going on at looking replacement of the current iron pipe work, which is far more susceptible to hydrogen embrittlement, with some of the newer PTFE, I think, is the main materials of the plastic. So looking at, as I said, diffusion of hydrogen through materials and that kind of thing. So in theory, yes, absolutely. Hydrogen can be blended into the gas network up to a certain point. At a certain point, the characteristics of the natural gas stop dominating, and the hydrogen characteristics will start to dominate. These are all areas of active research. My understanding is that from conferences I've been to is that there's no fundamental concerns or things that cannot be managed or potentially engineered. There's no kind of fundamental physics or chemistry that can't be overcome, and it's whether it can be from an engineering point, can it be managed from an engineering point and bled through. And my understanding is National Grid has said that they will effectively act as a sort of an ultimate off-taker for hydrogen to blend into the network. That is not from a decarbonising point of view. They're just there to create a market, because it's one of the challenges for a lot of the green hydrogen production. So if people want to trial green hydrogen for, say, decarbonising steel production or to replace for ammonia production, there's very few readily available green hydrogen sources. And part of that is because the finance market is very difficult to raise finance because there's no ultimate off-taker. So National Grid has said that effectively they will act as a client of last resort or a buyer of last resort, just to help get the market going, to encourage investment in electrolyser production, to actually then allow there to be a market of green hydrogen to then support all these trials of application. So that's something. That's probably a slightly broader answer, but safety issues, absolutely, they are fairly well understood. There's active research and they should be able to be managed in the future.
Thank you, Ed. I think we have time for one more question to answer. So what role, if any, do you think byproduct hydrogen should have in the energy transition? Anyone wants to answer that question? I mean, just a quick note on that, I'm not sure about the byproduct hydrogen, but if we're talking about, just synthesizing other fuels from the hydrogen, so there are lots of activities at the moment, I know in the UK for the synthesizer of the this kind of like fuels that is derived from the hydrogen, and they can have a significant actually play in different sectors such as aviation. Okay, so
I'll try and answer.
Do you want to go to?
Yeah, Roger's question. I think this goes back to me and Ines being on this energy systems interest group. So I think there is a move for policy to be led more like that. So the network system operator is definitely trying to approach this, and I think this has been one of the big challenges. Is that historically there's been an electrical grid, there's been a gas grid. There is actually a chemical grid. A lot of people don't realise that. There is actually ethylene and other things are piped around the country. And I think they're actually moving towards that more integrated picture, including things like other large-scale electrical users and that kind of thing. I think that the challenge, Roger, is that a lot of people tend to focus on like the end picture, the end architecture, rather than maybe incremental stages. And it's working out how we kind of go through that. And this group that me and Ines are members of is intended to try and help with that, to provide government and people access to people with systems engineering knowledge and capability who are involved in the energy transition sector to try and take that approach. And the simple answer is that it's a really messy, big problem. And I think Ines's point around that, it can become incredibly complex if you let it, and it's trying to find practicable ways of approaching the problem, breaking the program up into kind of manageable chunks or questions that can be answered. And yeah, absolutely, all these other things we talk about, industrial and domestic heat and all these kind of things and how we organize that. But there is, we are moving from a centralized energy architecture to a distributed energy architecture. So we're moving to quite different energy architectures, which is all the work that Michael and everyone else has been doing. And that's my systems engineering hat back on. But yeah.
Thank you very much, Ed. We are over the time now, so I just wanted to ask all the speakers again for the interesting presentations, and thank you all for joining this webinar. I hope that you enjoyed the webinar and also you found it useful. Thank you very much again for your time and presentation. Thank you. Cheers.